For the last in-class problem, it covers computation of a drag force, actually a lift force, over an object in an viscid flow. This is a homework problem, so I won't go into too much detail on this, but I'll give just some thoughts. The object is a quonset hut. I put a link in there to show you what it is. It's basically a portable military unit that can be used to store for people or store goods in. It can be put up and put down pretty easily. It's essentially a half cylinder in shape, and in our case the flow is going to come up, go up and over the hut, and then pass on. We're going to consider no variation in the span-wise direction, which is B. The hut has a radius of dimension A. So we can focus on the two-dimensionality, and we'll just multiply out the span-wise component. You are given a velocity field. The velocity field is written in polar coordinates. So if I have my arc here, here's x, here's y. In polar coordinates I have my radial coordinate, and I have my angular coordinate here, my theta coordinate. It's just a separate orthogonal coordinate system. In this case, theta is measured from the positive x-axis here, and the hut goes from 0 to pi. And again, this radius is capital R here. The velocity field that you're given is that the radial component is along the hut is equal to 0. So there's no flow normal to the hut, and the theta component, angular component, is equal to minus 2u infinity sine theta. The minus sign because you can see when we get to the top of the hut here, this radial vector is pointed backwards, but we want a positive velocity. We can see it's symmetric on either side. Our sine theta is symmetric about pi over 2 rather. Pi, sorry. So when we look at what this implies is the flow comes in, its sine phi is 0, we have 0 velocity. It accelerates to twice the free stream. It decelerates back to 0, and then it accelerates back to free stream. This is an inviscid problem. This should bother you when you look at it. You might imagine, well, the flow should separate over that. It couldn't stick to it like that, and that's true. We're assuming this is inviscid. This is an inviscid flow. So what we want to know is what is the lift on this structure? What is the lift force? And that is the force in the positive y direction, normal to the free stream. And what is the lift on the structure in terms of the parameters you're given? The lift in this case comes from the pressure. So we have to consider the pressure, but we have to be careful and make sure we consider the pressure on both sides. Not sure what that just happened. On both sides of the hut. You have pressure on the interior, you have pressure on the exterior, and we assume that there's a difference in pressure just leading to a net force. In this case, we were concerned with the up direction. In terms of the interior, we can assume that the pressure is equal to free stream, equal to the static pressure, just P infinity, 1 atmosphere on the inside. So the force contribution from the inside is going to be the integral from 0 to pi of P infinity times r d theta, that's our arc element, times sine theta, that's projecting it in the up direction, times b, that's going to be the length of the hut. Now I could pull P infinity, let's just look at this for a second where exactly this came from. If I zoom in, I have one differential arc right here. This is d theta, and this angle, and this length of this little surface here is r d theta, the arc length. And a pressure force here acts normal to this, can be decomposed in the up direction, that's times sine theta, and the x direction, which is cos theta, times sine theta times cos theta. I can see that on the other side I'm going to have same pressure acting like this, and thus these are going to cancel out. There's going to be no net x force due to the interior pressure and due to the asymmetry of the external pressure field on the left and right, or upstream and downstream, we will also have no net force in the x direction. Thus, there is no drag on the structure, and you can assure yourself that by actually computing out the pressure field if you want, but by symmetry you can make that argument. And that is the nature of two-dimensional inviscid flow. In 2D inviscid flow, steady, you have no drag. Steady 2D inviscid flow has no drag, and that's D'Alembert's paradox. We will have here, so we're going to compute this lift from the interior. Again, it's B. I'm going to pull the R. Oops, that's supposed to be B. Pull R out. I'm going to pull P infinity out, and I'm going to leave only the integral from 0 to pi of sine theta d theta, which is equal to 2. So we get 2 BR P infinity. Are the units correct? Yes, we have pressure times an area. That's a force. Good. So this is L on the inside. What is 2BR? 2BR, if we look back at our hut, is just simply the footprint of the hut. B, 2R. So it's the footprint of the hut times P infinity, and this shouldn't surprise us because we're dealing basically with what is the projected area of this surface in the L direction. This collapses onto 2BR. And we would get the same net interior force no matter what the shape of this would be. If the shape of the structure was this, but it still had dimensions 2R by B, we would get the exact same lift force because the projection is going to be the same. So that's the inside. For the outside, it's a little more complicated because you're dealing with a variation of the pressure over the top. So we're going to be integrating the outside pressure, which is a function of theta. And again, B times P theta of R sine theta d theta. That's the outside integral contribution to lift, and this is going to be a minus sign because positive pressure out here acts down. The trick is to first solve this using Bernoulli's in terms of the problem parameters. And then make that integral. You can see here that P theta is related through Bernoulli's to the velocity squared. The velocity contains a sine theta, so you're going to get a sine squared theta, and you also have a sine theta here. So at some point this integral is going to involve sine cubed thetas and other stuff. So you either have to run back to your calc book and see what is sine cubed theta from 0 to pi. The other alternative I would suggest thinking about, unless it's probably good practice to do this, but if you want to take a shortcut, you may be familiar with this, but the Wolfram Alpha web page is pretty amazing. I want to double check that it can do this. Let's have a look. So you go to Wolfram Alpha. I can't bring the browser up in this recording, but you go to wolframalpha.com. It has a search bar, what looks like a search bar on the web page, and you just type in there your equation. And here, if you type, just do it over here, integrate. I'm typing out the word integrate, sine caret 3x from 0 to pi. Let me just see if I can do that. It's computing. Okay, so I was able to do that. So what I typed in there was integrate, and then I wrote sine, S-I-N, put the caret there, x for the exponent, sine, sine cubed, that's the cubed, x from 0 to pi, and then hit return. Should get the same as your textbook gives you. That is not the integral you have to compute, but that's part of the integral you have to compute. So I'll leave it there to compute for you to compute the rest, but hopefully that gave you a